In the name of Almighty Allah, the most gracious, the most merciful. As Muhammad, peace be upon him, narrated, if anyone travels on a road in search of knowledge, Almighty Allah will cause him to travel on one of the roads of paradise. Hello everyone, this is Dr. Tariq Masood. Thank you very much for watching my videos and your wonderful support to make this channel a grand success. We are a family, a partner. Please share and subscribe our channel if you haven't done so far. We as a team can work together to convert challenges into opportunities and opportunities into success stories. These success stories can be monetized into value addition in the world by large. Thank you very much for your precious time. Today I'm going to discuss my lecture number 4 on fluidized catalytic cracking FCC unit, governing a pathway, delivering on commitment, differentiated performance, enabling profit optimization process. Before my lecture, I used to read a Quranic verse. Kala Rabbi Shirali Sadri wa Yassarli Amri Wahlalu Uqdatam min lisani Yafqahu qawli Allahumma Rabbi Zidni ilma. O my Lord, open my chest and ease my task for me, and loose a knot from my tongue that they may understand my saying. Allahumma Rabbi Zidni ilma. O Allah, advance me in my knowledge and true understanding. Okay, fluid catalytic cracking FCC unit, lecture number 4. Theoretical descriptions of FCC unit. Today we are going to discuss a main column section. We have already discussed reactor severity, regenerator severity, and feedstock quality in my lecture number 1 and 2 and 3. You can explore more about it in my earlier 3 lecture on FCC unit. Okay, key takeaway points from lecture number 4 on FCC unit. First, we are going to discuss main column bottom system, main column overhead systems, and then FCC catalyst. So in the main column bottom system, we will shed a light on HCU circulation, LCU circulation, and HNA circulation and their systems, product quality systems, stiffer vapor rate, lean oil flow to the absorber temperature, high pressure receiver temperature, pressure in the recovery unit, Okay, main column section variables. The main column section is equipped with circulating steams and heat exchangers. These are used to remove excess amount of heat from the main column and provide the internal reflux necessary for the fractionation. The heat exchangers of several of these steams is fixed by the heating duties of the gas concentration section equipment. Any change in the heat removal rate in one section of the main column compensated for in another. For example, if the heat removal in the circulating heavy naphtha circuit is increased, the column top reflux will automatically decrease since it is temperature controlled. Number 2, product compositions are affected by the column internal reflux states. These are changed by adjusting the top temperature or the side cut product draw rates. An increase in the top temperature or product draw will decrease the internal reflux below the draw, allowing heavy vapor to rise and thus produce a higher end point product. Quality improvement in the fractionation between steams can be obtained by increasing the internal reflux in the section of the tower between the two draw-offs. Since the composition is a function of temperature and a pressure monitoring draw, trade temperature is an excellent method of watching for changes in the reactor and main column operation. Okay, main column bottom system. What it demonstrates. The function of the bottom section of the main column are to desuperate the reactor vapors, to condense the bottom product, and scrub internal catalyst from the reactor vapors. The reactor vapors are desuperated by circulating a large volume of bottom materials over the lower trays, which are known as the disk and donut trays. Steam regenerator is the most flexible form of heat removal from the main column bottoms. Increasing heat removal by increasing steam generator will decrease the amount of vapors rising up the column, and less overhead reflux will be required to maintain gasoline and oil. The main column bottom's coking rate is a function of temperature and residence time under a normal operating conditions. In circulating, a main column bottom's heat removal must be achieved to keep the bottom temperature below the maximum of 365 degrees Celsius. Aqueous streams taken from the effluent side of the steam generations and returned below the disk and donor trays can be used to help cool the bottoms. Changes in reactor severity, charge stock composition, and charge rate may require an increase in quench rate to keep the bottom's temperature below 365 degrees Celsius. A hot bottom spillback to the disk and donor state is provided to maintain an adequate wash rate over the disk and donor trays when the unit throughput is reduced. Okay, the spillback rate should be adjusted as necessary to maintain a minimum wash rate of 230 meters cube per hour, which is approximately 120% of the feed rate. Residence time has a significant impact on coke buildup. Residence time in this context refers only to the time that the slurry spans in the column and not in the entire system. Once the slurry is removed from the column and passes through the heat exchanger system, the temperature is lowered and propensity for coking stopped. For convenient, UOP prefers to express residence time in terms of slurry circulation. To prevent a coke, this rate should not be less than 230 meters cube per hour. The main column bottom to storage rate is set by bottom's accumulation rate. This is a function of the charge rate and composition, catalyst type, and reaction severity. With the reactor cyclone design, a very little catalyst should be carried over to the main column. A measure of the catalyst and coke accumulation in the bottom is given by the BSW, which is a measure of its solid and water content. Normally, this should be about a 0.1 to 0.2 weight percent. Okay. Main column bottom system. The next is HCO circulation and product system. What it basically demonstrates here, the heavy cyclic oil circulation transfers heat to the gas concentration sections, debotanizers, reboiler, the naphtha splitter, a lower reboiler, and in the main column sections to the heavy naphtha stripper reboiler. Enough heat must be removed from the circulating HCO to produce a sufficient internal reflux for the HCO sections trays below the heavy cyclic oil return. If the circulating rate is reduced by the reboiler loads, the quantity of the internal reflux at the HCO section will decrease as more heat in the form of uncondensed vapor arises to the LCO section. This shift in heat up the column continues until eventually either the top reflux rate automatically increases to balance the heat removal, or until an increase in the circulating bottom heat removal rate is made to compensate for the decreasing in the heavy cyclic oil heat removal rate. It is apparent that the change in the heat removal rate from the section of the column must be compensated for the balancing change in heat removal from another section. Okay, next, LCO circulation and product system. Okay, LCO circulation and product system. Circulating light cycle oil transfer heat to the gas concentration sections, butanizers of feed exchanger, and the naphtha splitter upper reboiler. Its rate to determine by this exchanger a duty requirement and the sponge absorber lean oil flow rate. Heat removal from the circulating steam produces internal reflex in the LCO section below the return in a similar manner to that of the HCO return system. The light cycle oil product is drawn off and steeped in order to meet a flash point specification. Okay, next topic is HNA circulation and product system. Okay, HNA circulation and product system. Circulating heavy naphtha exchange heat in the heavy naphtha raw oil exchanger before returning above the HNA draw tray to provide internal reflex in that section of the column. In case that hot feed is processed in the FCC unit, heavy naphtha raw oil exchanger requires reduced heat duty. This is compensated by air cooling of the circulating HNA in heavy naphtha pump around cooler. The HNA product, heavy naphtha product, is steeped in the heavy naphtha steeper to establish the vapor pressure. Okay, main column overhead systems. A substantial amount of main column heat removal is done by the overhead condensing system. The tower overhead vapors temperature and pressure determine the end point of the overhead naphtha product. This overhead temperature resets the top reflex flow rate control to maintain the desired unstabilized naphtha endpoint. The reflex stream comes from the main column reflex drum. Column pressure is maintained by maintaining a column receiver pressure control. An overpressure vent to flare is used on a startup and in emergencies when the wet gas compressor in the gas concentration unit cannot handle the gas load. The overpressure vent valve is controlled by an independent pressure control valve, which is typically set at approximately a 0.035 bar G above the controlling pressure set point. The pressure is normally controlled by the wet gas compressor in the gas concentration unit. A signal is sent from a second pressure transmitter on the main column receiver to the wet gas compressor control system to maintain the desired pressure. Okay, next is the gas concentration section variables. Okay, what it demonstrates gas. Okay, gas concentration section variables. The purpose of the gas concentration section is to maximize LPG, that is C3, C4 recovery, while minimizing H2S contamination. The unit is controlled by observing the C3 content of the lean gas from sponge absorber and the H2O content of the LPG steam. In practice, as the C3 content of the lean gas increases, the H2S content of the LPG steam decreases, and vice versa. Okay, next is the steeper vapor rate. That is a part of gas concentration section variables. A steeper's variable. Okay, gas concentration section variable. First is the steeper vapor rate. The flow control in the steeper overhead vapor line is the primary control in the recovery part of the gas concentration section. Normally, all other variables are held constant, and this vapor rate is varied to control the H2S content of the LPG steam. The steeper vapor rate controls the flow of steam through the steeper reboiler tubes, increasing the steeper vapor flow and decreasing the H2S content in the steeper bottoms, but will increase the propylene and propane content of the lean gas from the sponge absorber. The vapor flow should be adjusted to give a minimum content of H2S in the debutanizer's overhead with minimal content of propylene and propane in the sponge absorber of gas. It is possible to build up a liquid cycle in the steeper and overload it with liquid. For example, should the steeping rate become excessive, the steeper vapor will contain heavier than desired components which end up as a liquid in the high pressure vessel. This will increase the feed rate to the stipper and increase the liquid load and consequently the pressure drop across the column. These conditions tend to increase a liquid internment back to the high pressure receiver, magnifying the problem. The best immediate action to rectify the situation is to drastically reduce the heat input to the bottom of the stipper by lowering the setting on the stipper vapor flow control until the upset condition is corrected. A sudden increase in hydrogen A sudden increase in the hydrogen sulfide level of the LPG steam should not be constituted as a being a result of the lower stripping alone. For example, if the sulfur content of the FCC unit charge increases, the H2S content of all the steam will increase roughly in that portion. On the other hand, if the H2S of the LPG steam is held constant by changing stripping rate, the propane content of the lean gas will increase. Okay, lean oil flow to the absorber. First is a primary absorber. Lean oil flow from the main column is not variable that operators can control. Recycled naphtha from the debotanizer's bottoms can be adjusted to increase C3, C4 recoveries. However, caution must be exercised to avoid a liquid flooding at high throughputs for all absorbers. Number second is sponge absorber. Increasing the sponge oil flow rate tends to increase the absorption efficiency of the sponge absorber. Changes in sponge oil flow rates have only a slight effect on C3 recovery, but the effect is more noticeable on the recovery of heavier components. Third is gas amine absorber. Increasing the lean amine flow will improve absorptions and decrease H2S and CO2 content in the suite of gas. Okay, next is absorber temperature. Okay, absorber temperature. While the absorber temperature is not normally considered to be variable, absorption is favored by low temperatures. The intercooler are generally operated around 40 degrees Celsius. Okay, high pressure receiver temperature. Generally, the high pressure receiver temperature is held close to 40 degrees Celsius. Variations of this temperature will result in a large variation in the stripping and absorption rates. Okay, pressure in the recovery part. The gas amine absorber pressure control maintains a constant pressure on all vessels in the gas concentration unit, except the debotanizers and naphtha splitter. The system pressure is a secondary control which, though normally not used for day-to-day operations, can be used to keep the necessary stipper vapor rate in the convenient range. It may sometimes be desirable to lower the system pressure when the cracking unit swings to a high sulfur charge stock. The system pressure must always be high enough to charge the debotanizers. Okay. Next, we are going to discuss FCC catalyst management system. Okay. Okay. FCC catalyst is a fine powder, generally smaller than most refinery catalysts. Its particle size distributions is in the 10 to 130 macron range. Through the use of fluidization medium such as air, hydrocarbon, vapors, or steam, the catalyst fluidizing media mixtures can be made to behave as a liquid. Fluidized catalyst can assume a level surface similar to that of a liquid as it does in the reactor and regenerator. It can be made to flow through a pipe as in the case of standpipes and reactor risers. In essence, it is like liquid steam. It is the principle that permits the circulation of catalyst between the reactor and regenerator. FCC catalyst is used today are composed primarily of the oxides of silicon and aluminum. Other elements often present including sodium, calcium, magnesium, and member of the rare earth family such as lithium and cerium. The source of catalyst activities is an acid site, which enables the catalyst to crack the large oil molecule selectivity to lighter material. FCC catalyst has a regular zeolite structure. The basic building block of zeolite is the silicon tetrahedrons, a silicon atom bound to a 4 oxygen atom. Aluminium can also form tetrahedrons with oxygen and replace with SiO4 in the zeolite structure. When aluminum oxide replaced with silicon oxide, a negative charge results for every aluminum atom. To maintain electrical neutrality, a positive ion, or usually hydrogen, must compensate for the negative charge. It is believed that this is the catalyst active site. The silicon aluminum tetrahedrons are linked to each other by sharing oxygen atom to form a cubo-octahedrons called a sodalite unit. The two zeolite type, X type and Y type, are the primary interest for FCC catalyst. The two zeolites are identical in structure and differ slowly in their Si-aluminum ratio. These zeolites are formed when sodalite units are joined by hexagonal prisms on their hexagonal faces. The resulting structures creates a mass of a channel and cavities called alpha and beta cages. Beta cages or cavities creates a mass within the sodalite unit. Alpha cages are the cavities resulting from interconnecting sodalite units. Typical fresh FCC catalyst specification I'm going to discuss on my next slide. Okay, typical fresh FCC catalyst specification. First chemical properties, then we'll discuss physical properties. First is the chemical. Aluminum oxides 17 weight percent, sodium oxides 0.3 weight percent, and trion oxides that is 2.7 weight percent. Physical properties: surface area 300, pore volumes 0.43, apparent block density ABD 0.74, average particle size APS is 70 macron and macro activity is 79. Okay, conclusion. Today we have discussed main column bottoms and main column overhead system and FCC catalyst. In the main column bottom we have discussed HCU circulation, heavy cyclic oil, light cyclic oil, and heavy naphtha circulation and product systems. Okay, on later on we have discussed main column overhead system, steeper vapor rate, lean oil flow to the absorber temperatures, high pressures, severe temperature pressures in the recovery unit. And then we have discussed FCC catalyst. Okay, next topic, unit process description very soon. These are a few references. Okay. Please do not hesitate to send me your feedback, comments, t.sood.dear@edu. Thank you very much for your precious time. Please stay at home, stay safe, inspired, and